Modern maritime operations face an invisible, saturated battlefield. Out on the tactical edge, isolated platforms endure constant electronic warfare, from broadband jamming to precise spoofing. These environments are actively contested and frequently DIL, disconnected, intermittent, and low bandwidth. A tactical node cannot simply ping a cloud server to download the latest threat signature updates. When a conventional wideband receiver encounters strong interferers, it faces two distinct failure modes. The first is physical saturation. Strong jamming signals overdrive the analog front end, blinding the receiver entirely. The second failure mode is digital paralysis. Even if the wideband capture survives the analog stage, it generates a massive digitization load. This tidal wave of data overwhelms the local processors. This presents a paradox. A disconnected edge node must cut out an unknown zero-day threat, but it lacks external signature libraries and the local compute power to analyze the full spectrum. The solution is an entirely new architecture, the PTCP Omnibus Cage. This system functions as a physical-to-digital co-design. It merges a highly resilient, coherent RF photonic front end with an advanced tensor network control layer. By integrating these layers natively on the edge node, the architecture completely eliminates the requirement for cloud-dependent threat databases. Instead of scanning for known malicious code signatures, it continuously evaluates the physical geometry of the incoming signals. To survive a disconnected environment, we have to abandon software-only cyber defenses. The solution requires a unified electro-optical and topological system. This diagram maps the complete PTCP architecture, tracking the signal path from physical capture straight through to digital control. The signal's entry point is a standard nominal 50-ohm antenna input, capable of receiving wideband high-frequency, RF, and APNT data. In a standard receiver, electrical downconversion at this stage introduces severe nonlinear distortion the moment heavy electronic warfare jamming hits the antenna. To prevent that distortion, the system executes an immediate handoff, passing the raw RF signal directly into the photonic layer. Here, the wideband RF signal modulates a remote optical carrier. This relies on a highly efficient, low-voltage, sub-1 volt VPI coherent modulator path. Converting the signal into the optical domain yields exceptionally high spurious-free dynamic range, or SFDR. The link maintains clarity even under extreme interference. The physical layer then outputs pristine, polarization-managed I and Q optical channels, delivering them cleanly to the digital backend. By handling polarization management directly within this module, the design avoids the mechanical fragility of relying on polarization-maintaining fiber for routing throughout a ship. This electro-optical transition mathematically insulates the receiver from the analog saturation vulnerabilities that cripple conventional wideband systems. The photonic layer preserves wideband signal fidelity perfectly, but it also outputs a massive high-resolution data stream that threatens to crush standard edge processors. The optical I and Q channels are ingested here at the digital processing stage. Tracking high-resolution telemetry as a dense table scales at an exponential rate. This creates a severe data explosion known as the O of n to the power of d scaling problem. Low-swap maritime nodes cannot process that volume. The software countermeasure to this bottleneck is the pattern-of-life tensor train. The tensor train mathematically compresses high-dimensional features, like time, frequency, and phase, into a low-rank probability tensor. It continuously encodes local network state and APNT timing residuals directly into this compressed format. Bounding the memory overhead allows the system to learn the baseline, normal RF behavior entirely on local edge hardware. This local learning achieves the primary operational goal, removing all reliance on cloud-delivered threat intelligence. Tensor compression brings the processing requirements of high-bandwidth RF photonics within the functional limits of tactical edge hardware. If the system isn't using threat signatures, how does it identify a zero-day jamming attack or a spoofing attempt? It routes the compressed data into the topology reconstruction engine. The system stops evaluating discrete, linear traffic logs. Instead, it reconstructs the RF links, photonic bonds, and network telemetry as a topological graph. The core principle is physical. Unknown interferers, or cyber compromises, natively disrupt the information geometry of this graph. These attacks warp the graph, manifesting as measurable shifts in cut capacity and sharp anomalies in graph curvature. The system calculates the exact severity of these topological deformations to generate a metric called the D-topo defect score. D-topo ignores the actual content of the malicious signal. It flags the anomaly strictly by its physical disruption to the local data flow. Topology native scoring turns the network's own structural geometry into an unsupervised intrusion detector. When the D-topo defect score crosses a critical threshold, the system triggers an active response. This initiates the geometric kill switch. The switch enforces a strictly bounded, reversible quarantine protocol to isolate threats without affecting healthy traffic. It executes automated control actions like adaptive notch filtering in the DSP, draining compromised traffic, or physically isolating specific sensor paths. These actions strategically contain the blast radius of the interference, stopping it from moving laterally through the rest of the shipboard network. Crucially, all containment actions operate under a safe policy envelope that explicitly exempts a priority mission allow list. This allow list guarantees that vital position, navigation, and timing data, along with command and control communications, continue to flow uninterrupted while the defect remains quarantined. This policy envelope ensures an edge node can compartmentalize anomalies and preserve core mission services under sustained electromagnetic or cyber pressure. The result is a complete closed loop, linking physical capture directly to digital quarantine. This gives the Navy true network autonomy in heavily contested SATCOM-denied environments. The wideband RF photonic front-end provides unmatched linearity and interference resistance of the physical layer. The pattern-of-life tensor control layer provides bounded memory intelligence, stripping away the need for external cloud connectivity. This moves maritime operations away from relying on passive sensors waiting for instructions toward geometry-aware edge systems that adapt in real time. It delivers simultaneous integrated protection against both physical signal jamming and cyber-physical topology attacks. Beyond individual ships, this architecture scales to secure distributed maritime platforms, offshore energy operations, and future autonomous shipping networks. The PTCP Omnibus Cage ensures maritime superiority by making the tactical edge structurally immune to the unknown.